Talked about thunderstorms. Let's talk about what happens when a thunderstorm goes extreme. So far what we've actually talked about are pretty typical thunderstorms. They happen every day. They're honestly present around much of our country, definitely during the summertime. They form from heat and moisture. They have a very short life cycle, and really they don't pose too big of a hazard. They're mainly a nuisance, and as long as you just know to take proper precautions, usually they're not a big deal. However, some thunderstorms take it another step, and they become what are called severe thunderstorms. Now, severe thunderstorms are extreme weather, and they form from normal thunderstorms that have something added to them. And that something is usually some kind of vertical wind shear. And vertical wind shear is just a fancy term for winds changing either in direction or speed with height. These wind shears, and we'll talk more about wind shear in the next lecture, these wind shears promote updrafts. And if you recall from the last lecture, updrafts are the food of the thunderstorm. If you don't have an updraft, you aren't going to have a thunderstorm. Well, in a severe thunderstorm, vertical wind shear prevents the downdraft from cutting off the updraft. And so the thunderstorm just keeps growing and growing and getting more intense, and it just continues on until something stops it. Now, this allows the storm to just continue to strengthen and continue to strengthen. And as a result, these storms can become very powerful. These storms are the ones that produce the largest hail, the highest winds, the most lightning, and tornadoes. Rainfall rates can become extremely high in these kind of storms. Hail can become extremely large, so those softball and baseball-sized hailstones I showed in the last lecture, those come from severe thunderstorms. Those microbursts, those high winds, those come from severe thunderstorms, and tornadoes come from severe thunderstorms. Now, they also produce some pretty interesting clouds, things such as wall clouds and mammatus clouds, and I have a few images I'll show you later in this lecture. Now, these thunderstorms can actually become very tall, especially if there's enough fuel that allows that updraft to continue shooting upward. And that creates what's called an overshooting top, and then I'll show you an image of one in a few slides. Now, as a result of these strong updrafts, and as a result of them being allowed to just keep going and keep going, this allows for hail to become extremely large. And then if there's enough shear that's present in the atmosphere, and again, we'll talk more about what shear is in the next lecture, severe thunderstorms can even produce tornadoes. Here's how a severe thunderstorm looks like on a radar. So we've talked about radar briefly in this class, and radar is just one tool that meteorologists use to identify different weather phenomenon, specifically the presence of rain, snow, sleet, hail, and so on. Well, here, this radar is actually indicating a line of severe thunderstorms. The severe thunderstorms are usually highlighted in areas of yellow, orange, and red. Those represent the heaviest precipitation and oftentimes also represent hail. Now, in these severe thunderstorms, the updrafts are so strong that they also produce very strong downdrafts. Now, once the air from those downdrafts reaches the surface of the earth, and let me get out my little pin here. That's not going to work on this image. Let's try white. What happens is once that air reaches the surface, it then spreads outward. And that produces what's called outflow. And on the boundary of this outflow, this is the gust front that we talked about in the last lecture. this outflow boundary can actually be shown on radar by looking at dust that it's picked up. And so this whole area here, this is a line of dust that has been picked up by these severe thunderstorms. And so when you see a strong outflow boundary like this, and in the center of it, you see these areas of red, orange, and yellow, that represents some very severe thunderstorms. Now, there are different types of severe thunderstorms. Some aren't as dangerous as others. The first type of severe thunderstorm is what's called a multicell thunderstorm. Here, you basically have thunderstorms going through different stages of the life cycle, and they're feeding off of one another. And wind shear allows for these to form. And the reason why wind shear allows for these to form is as one thunderstorm begins to fall apart, this wind shear allows that updraft to then feed into a new thunderstorm, allowing severe thunderstorms to develop. And what actually happens in these multicell thunderstorms is if that if that updraft is tilted straight upwards, it can actually allow for air to rise so quickly that it blasts through the top of the tropopause and into the stratosphere, producing what's called an overshooting top. So here's an image of a multicell thunderstorm, and here's what this wind shear is. Wind shear happens when winds change direction and speed with height. This little short arrow pointing in this direction represents a weak wind blowing from right to left. As you begin to travel upwards in the atmosphere, the wind shifts from right to left to right, and the arrows become longer and longer. These indicate stronger and stronger winds. So the wind didn't just change direction, it also changed speed with height. This allows for this updraft to continue to sustain itself. It prevents the downdraft from cutting it off. Now, this allows this updraft to become stronger and stronger, and eventually it can become so strong that, as I mentioned earlier, it can actually blast through the tropopause, producing, and let me highlight this up here, producing this overshooting top. It basically looks like the little poof ball on Stan Marsh's hat. Or if you don't watch South Park, if you've ever had a beanie with a little poof ball at the top, it looks kind of like that. Here's an image of multicell thunderstorms. And here what you actually have is you have one thunderstorm over here that's in the early stages of its life. You have another thunderstorm here in the center. This is in the mature stage. And then this thunderstorm here is in the dissipating stage. And as this thunderstorm falls apart, it feeds into this thunderstorm. And then this thunderstorm is feeding into the growing thunderstorm next to it. So they're feeding into one another. Now, commonly at the base of some of these multicell thunderstorms is something called a shelf cloud. Basically, this happens due to that wind shear. As air is sinking, it reaches the surface, and the wind shear causes the air to spiral like this, creating what almost looks like the base of a spaceship. Now, most multicell thunderstorms are part of what's called a squall line. And squall lines are very common ahead of cold fronts. Usually roughly 100 to 300 kilometers, that's approximately 60 to approximately 200 miles, that's about right, 60 to 200 miles ahead of a cold front. And these particular storms form in the warm sector of a mid-latitude cyclone. This is where all the heat and moisture is. And as the front is approaching, it allows new cells to form as old cells die. So it looks something like this. The front is, and I'll pull out a blue pen here, the front is back here. Yeah, it's really not easy to see, but can't blame me for trying. So the cold front is back here, and ahead of the cold front you have substantial amounts of heat, substantial amounts of moisture, and substantial amounts of rising air. And so they can create this squall line of severe thunderstorms. Now, why does the squall line form this far away from a cold front? We're not 100% sure yet, and we're still learning more and more about squall lines. Now, the strongest and most hazardous thunderstorm is what's called a supercell thunderstorm. So what we've already talked about with severe thunderstorms are multicell thunderstorms and squall lines. Those are thunderstorms that travel in packs. Supercell thunderstorms, on the other hand, are usually lone wolves. In the case of a supercell thunderstorm, you have no cutting off from the downdraft. The updraft continues to grow and grow and grow. And as a result, these thunderstorms can last hours and hours and hours. They can last a very long time. And these updrafts in these thunderstorms can become intense, resulting in the most damaging winds, resulting in, since you have all this warm rising air and all this warm moist air, the heaviest rain, the greatest hail. But you also have one other thing that isn't common in multicell and squall lines, and that's the presence of rotation. And that's what makes a supercell a supercell. Rotation is what makes a supercell a supercell. So here's what happens in a supercell thunderstorm. In a supercell thunderstorm, at the surface of the Earth, you have air feeding into the thunderstorm. That's the updraft. Meanwhile, wrapping around the supercell, because of this wind shear, wrapping around the supercell is these two downdrafts. On the front of the supercell, you have what's called the forward flank downdraft. This is where most of the rain occurs, in the forward flank downdraft. Then behind the updraft, you have what's called the rear flank downdraft. This rear flank downdraft brings air from the middle part of the troposphere, and it brings it wrapped right around the updraft. And this rear flank downdraft has air that's pretty cold compared to the warm rising updraft. Therefore, you get a great temperature difference. A great temperature difference leads to a great pressure difference, if you recall from the two-column model. A great pressure difference leads to wind. And therefore, wind becomes extremely strong in this area where the rear flank downdraft wraps around this updraft. This also creates rotation in the updraft, producing what's called a mesocyclone. If this mesocyclone can stretch to the base of the cloud and down to the surface, it creates a tornado. Now, a better image of a supercell can be looked at if we look at it from the top. So here is a supercell thunderstorm looking at the top. Rather than looking at a vertical cross-section like this, we're going to look at the top downwards. And here's what you get. On the surface, you have lots of warm, moist air. This warm, moist air flows into the thunderstorm, like so. Meanwhile, wrapping around the thunderstorm are these two downdrafts. In the forward flanking downdraft, you have the heaviest rain and the hail. In the rear flank downdraft, you have much drier air, and it's typically rain-free. But this forward flank downdraft and this rear flank downdraft wrap around the updraft, producing this mesocyclone. Now, this mesocyclone is the beginning of a tornadic thunderstorm. And we're really worried about these when we actually identify them, because these particular thunderstorms are capable of producing tornadoes. Now, I mentioned earlier that we can identify thunderstorms by looking at radar. How would one of these look on a radar? Well, it would look something like this. So here is a supercell thunderstorm identified on radar. It looks like a little comma, like an upside down comma, with the tail of it fanning outwards. Here's what happens here. So it's already diagrammed pretty well, but let me show you what happens. So warm air comes in right there. That warm air rises, and because of that, you have rising motion here. You don't have any rainfall right there. Meanwhile, the forward flank downdraft wraps right around it. Then finally, you have the rear flank downdraft back here, and you get this rotation that develops. And that rotation is what gives you the tornado. Now, what are some of the pieces that we can identify here? Well, first off, we can identify the presence of very large hail and heavy rain in this area here. This is because of the forward flank downdraft. The area back here is rain-free. The area in the rear flank downdraft is rain-free, and then the area where the updraft is rain-free. Now, how do we get this wind shear? How do we get these different downdrafts that flow into each other? How do we get conditions like this? Well, wind shear has to be present at different layers, different levels of the atmosphere. And there are actually 5 particular layers that we look at. We look at the surface, then we look at the 850 millibar level, which is about 5,000 feet above the surface, then the 700 millibar level, which is about 10,000 feet above the surface, the 500 millibar level, which is about 18,000 feet above the surface, and then the 300 millibar level, which is about 30,000 feet above the surface. All right. On the surface, we usually have warm, moist air coming from the south, southwest, and southeast. Like so. When we actually, and this air is very warm. As we begin to rise up in the atmosphere, near the 850 millibar level, we have more warm, moist air shooting upwards in what's called a low-level jet. It's shooting from south to north. As we begin to rise up to the 700 millibar level, we begin to get cooler and drier air that is coming in from the southwest. Then higher up, we have cold air coming from the west and from the northwest. So we get this situation where near the surface, winds are coming in from this direction. At 850 millibars, they're coming in from this direction. At 700 millibars, they're coming in from this direction. At 500 millibars, they're coming in from this direction. And at 300 millibars, they're coming in from, let me get that. They are coming in from this direction. Well, if I'm a parcel of air, and I've started at the surface of the Earth, and I'm beginning to rise in the atmosphere, what's actually going to happen is I'm going to start by blowing this way, and then I'm going to quickly turn this way. That's rotation. And so rotation begins to develop, and it's this rotation that fuels these mesocyclones. It's this rotation that fuels these mesocyclones. So this is how supercell thunderstorms form. Now, in the next lecture, we're going to go a step further, and we're going to talk about how these supercell thunderstorms produce tornadoes. Until then, I'm Terrence Mullins. Thank you for watching.